Hello viewers, welcome to this module Serial Autocorrelation Part 3. In this module we will take a look at some more tests on serial autocorrelation. To begin with, we consider the k variable linear model with ARP scheme. So, the linear model k variable model is shown as yi regressed on an intercept and variables x2 through xk with the random disturbance term ui, which has ARP scheme. So, ui depends on I minus 1 through I minus p with another term, that is epsilon I, which is independent, normal mean 0 and sigma square epsilon. And the second equation is autoregressive of order p. So, combining we have this regression where y is regressed on an intercept x2, x3 up to xk, and in place of ui we have rho 1 ui minus 1 through rho p ui minus p plus epsilon I. So, let us now see how we can detect the presence of serial autocorrelation. So, the LM test for this consists of the null hypothesis, that is rho 1 equal to rho 2 equal to rho p equal to 0 against the alternative hypothesis, that is at least one of the rows is not equal to 0. So, this is known as the Brush-Godfrey LM test and it has the following steps. First, we regress yi on x2 right up to xk with an intercept, and we use the ordinary least squares method and obtain the residuals, that is we obtain the EIs. Then in the next step we regress EI on all the variables in the regression, all the x variables in the parent regression. So, we regress EI on all the x variables in the parent regression plus EI minus 1, EI minus 2 right up to EI minus p along with an intercept. This is the auxiliary regression. The number of observations here is n minus p because we lose some observations since we are considering I minus 1, I minus 2 right up to I minus p. So, effectively in the auxiliary regression the number of observations is n minus p. Now, from the auxiliary regression we compute the test statistic n minus p r square. This r square is the r square, that is the square of the multiple correlation coefficient obtained from the auxiliary regression, and the test statistic n minus p r square follows a chi-square distribution with p degrees of freedom. So, if the computed value exceeds the critical value, then we reject the null hypothesis, that is all the rho i's are equal to 0, or otherwise we accept the null hypothesis. One thing has to be kept in mind, since there are k plus p regressors in the equation, that is beta 1 then x2 up to xk and EI minus 1 right up to EI minus p. So, there are k plus p regressors and the number of observations is n minus p. So, n minus p must be at least equal to k plus p, which requires that n must be at least equal to k plus 2p. Now, after having detected autocorrelation, we now look at the method of estimating. If there is autocorrelation, then how do we estimate the model? Once again, we look at the original model, we look at the autoregressive pth order scheme, and then we use an iterative method to come to the estimated model. This iterative method is very similar to the Cochrane-Orcutt iterative method that we used in an earlier module when we discussed serial correlation. Here, the major difference is we are considering the original regression to be the k variable linear regression, and we are considering the autoregression to be ARP scheme. So, once again the original model is given as earlier, y regressed on intercept x2 up to xk plus u, where u is autoregressive of order p. So, ui depends on ui minus 1, ui minus 2, right up to ui minus p plus epsilon I, and epsilon i's are independent, normal 0, mean 0 and variance sigma square epsilon. Now, the crux of the estimation process depends on a transformation of the model. We have earlier learnt that if we apply ordinary least squares to a model which has been detected with autocorrelation, then although estimates are biased, the estimates are not efficient, the minimum variance property is lost. So, we transform the model into another form such that the transformed model is amenable to the use of ordinary least squares. So, how do we transform the model? The important cue is, if we subtract from ui the terms rho 1 ui minus 1, rho 2 ui minus 2 and up to rho p ui minus p, if we can subtract these terms on the right hand side from the term on the left hand side, then we are left with epsilon I, which follows the properties of the classical model. That is, there is no more any serial correlation or heteroscedasticity or any other departure from the classical framework. So, that is exactly what we do. So, you can see on the right hand side, if you have ui, and you can see on the right hand side minus rho 1 times ui minus 1, then again minus rho 2 times ui minus 2, and right up to minus rho p times ui minus p. So, if you can do that, then effectively you are converting these ui's into sigma I. But to do that, what we need to do is a simple operation, that is, first we write the mother model, then we lag it by one period. So, the second line we have yi minus 1, and on the right hand side everything inside the parenthesis corresponds to yi minus 1. Then we multiply both sides with rho 1 and subtract from the first row. Similarly, in third row we lag it by 2 periods. So, we write yi minus 2 on the right hand side, again within the parenthesis all these terms correspond to yi minus 2. Now, how do we transform? We multiply both sides left and right of the third line by minus rho 2, and we continue doing that till we reach I minus p. So, we stop at I minus p because that gives us ui minus p, and the autoregression is of order ui minus p. So, last row you can see yi minus p on the left hand side. On the right hand side within the parenthesis you have the corresponding expression for yi minus p, which is now multiplied, both sides are multiplied by rho p and subtracted from the mother model. So, that gives us the transformed model, where on the left hand side we have yi minus all the lags of yi up to t I minus p up to I minus p, and these lags are multiplied by the corresponding autoregression coefficients rho 1 or autocorrelation coefficients rho 1, rho 2 up to rho p. Similarly, on the right hand side, instead of beta 1 we have 1 minus rho 1 minus rho 2 etc. Then we have beta 2, instead of simply x2i we have x2i minus x2i minus 1, x2i minus 2 up to x2i minus p, each of these terms multiplied by their corresponding autocorrelation coefficients rho 1, rho 2 etc., and that goes right up to beta k. So, beta k and not into xki, but xki minus rho 1 xki minus 1, rho 2 xki minus 2, right up to rho p xki minus p. And you can see now that the transformed model is left with a disturbance term sigma I, which follows the classical properties. So, on this model we can safely apply ordinary least squares. But before applying ordinary least squares on this model, we need to find out the rows, which we do not know, rho 1, rho 2, rho p. So, that we do not know. Therefore, we have an iterative method. What are the steps? First, we go to the mother model and we regress y on intercept x2 up to xk using the ordinary least squares method, and then we obtain the residuals EIs, because the rows will depend on actually UIs, but UIs are not observable. So, the proxy for UI is EI. So, from the mother model in step 1 we obtain EIs. Step 2 we regress EI on EI minus 1, EI minus 2 up to EI minus P. The reason is the model is UI regressed on UI minus 1 through UI minus P, but the U terms are not observable. So, proxy for those are the errors of estimation EI terms. So, we regress E on the lags up to the pth lag, and there is no constant term because the autoregressive scheme does not have any constant term. And then we obtain ordinary least squares estimates of rho 1, that is rho 1 hat, rho 2 hat up to rho k hat. Now, these rho hats can be substituted in this transformed model. Once we substitute these rho hats in the transformed model, we obtain a model where the remaining disturbance terms epsilon I follows the properties of the classical model. So, on this transformed model with these rho i's substituted by rho I hats, we can now apply ordinary least squares. So, when we do that, you have the transformed model with rho hats instead of rows, and here we can apply ordinary least squares, and from here we can obtain the betas, estimates of the betas. So, from this regression we can obtain the estimates of the betas. Now, these are the second round estimates of the betas, because as you will have noted, in the first round we already estimated the model using ordinary least squares, and from there we obtained EIs. So, now this is the second round estimate. What do we do with that? We go back to step 1. The second round estimates we put here, and we get y hat second round, that gives us second round estimates of the errors. So, the beta hats in the second round are placed here, and y minus those beta hat xi's gives us the second round estimate of the EIs. Now, when we get the second round estimates of the EIs, okay, we go to step 1 and we get the second round estimates, as you can see. Once we get the second round, then from the second round we again regress EIs on EI minus 1, EI minus 2 right up to EI minus P to get the second round estimates of the rows. So, as you can see, substituting the second round estimates in the betas, we obtain the second round residuals. This is second round of the values EIs, and repeat step 2, that is second round EI on EI minus 1 up to EI minus P. Once we do that, we will again get the second round estimates of the rows and again put in that transformed model to get the third round estimate of the betas. We continue iterating like this till, you can see in step 6, till we produce EIs such that the sum of square of errors calculated from successive iterations differ by very small magnitude, that is maybe differ by less than 0.1%. So, if that stage is reached, that means then we say that there is a convergence and we stop there, and that is the final, that stage gives us the final estimate of the betas. Now, from here, next thing that we go into is how do we take care of autocorrelation when one of the regressors is a lagged dependent variable. Up until now, what we have done is we have regressed y on x variables and some disturbance term which may be classical or it may be heteroscedastic or it may be serially correlated and so on. Now, we are considering the case where one of the regressors on the right hand side consists of yi with a lagged value, whereas yi is the regressand. So, this is the case when we have lagged dependent variable. Okay. So, we have lag dependent variable and the model, simple model is yi regressed on yi on y, maybe this is I minus 1, yi on yi minus 1 and xi, yi on yi minus 1 and xi, and where ui is autocorrelated of order 1. So, you can see that since yi minus 1 is on the right hand side, it is one of the regressors. So, yi depends on ui minus 1 and I minus 1, yi minus 1 will also depend on ui, because ui minus 1 and ui are both correlated. I repeat once again. So, ui depends on ui minus 1 and yi minus 1, my dear viewers, this is yi minus 1, this is I minus 1. So, yi minus 1 will depend on ui minus 1, okay, because when you have yi minus 1 here, you will have ui minus 1 here. So, yi minus 1 will depend on ui minus 1 and ui itself depends on ui minus 1. So, there is some correlation between yi minus 1 and ui. That means, the regressors and the random disturbance terms, they are correlated. So, this violates one of the basic assumptions of the classical linear regression model. That is, the regressors, that basic assumption is that the regressors are uncorrelated with the disturbance term. So, that assumption is now violated, and therefore, if we apply ordinary least squares, we will not only get biased estimates, but even if we increase the sample size, that bias will not get corrected. Okay. So, that is a very fundamental violation, and therefore, we cannot use OLS and we cannot use our standard Darwin-Watson test statistic that is based on OLS method. So, under this condition, ordinary least squares leads to not only bias estimates, but also inconsistent estimates. As I said, when the sample size increases, that bias does not go away. So, it is an inconsistent estimate. So, what is the way out? The way out is, or before the way out, just a little bit more on that problem. So, as the sample size increases, the estimate of rho hat, that approaches not rho, but rho minus a constant term a. So, that term a is defined here, and therefore, our Darwin-Watson test statistic, which is d is equal to 2 into 1 minus rho hat, that will move towards the value 2, because when rho hat gets underestimated, rho hat becomes smaller and smaller, because rho hat tends to rho minus a. So, rho hat becomes smaller and smaller. So, it will be closer to 1, therefore, d will be closer to 2, and when d is closer to 2, we say that there is no serial correlation. So, we will not find any evidence of serial correlation, whereas actually there may be evidence of serial correlation. Reason is that here the estimate of rho is not a consistent estimate. So, what do we do? We use Darwin's H test, that involves Darwin's H statistic. And what is that H statistic? That is, H is given as rho hat times, within second brackets, the ratio of n. Actually, here this n is n minus 1, because we have first order autocorrelation. Effectively, this n will be n minus 1, but generalized way you can write n divided by 1 minus, again this n should be n minus 1, 1 minus n times the estimate of the variance of alpha hat, the whole thing to the power half. So, this is rho hat, then square root, within the square root you have the ratio n divided by 1 minus, in the denominator you have 1 minus n times the estimated variance of alpha hat, and that H tends to a normal distribution with mean 0 and standard deviation 1. So, that tends to be a standard normal variate. So, n is the sample size. So, n is the sample size, effectively, as we saw earlier, due to lags, this n will be reduced by 1. But again, once we calculate this H, we can compare it with the critical values of the standard normal distribution, and we will reject or accept according to our standard test procedure. But there is another problem here, that is, this cannot be applied if n times estimate of variance of alpha hat exceeds 1. So, you can see the denominator, this denominator, if it exceeds 1, then we cannot use this. And therefore, there are alternative tests, namely Darwin's alternative test, but a more general form of that test, or a generalized test comprises of a regression of y on p lags of y itself. That is, we have lagged dependent variables generalized up to order p, and then we also have other x variables plus u. So, let us take a look at that test. That is the Brush-Godfrey LM test for higher order autocorrelation when there are several lagged dependent regressors. So, we have yi regressed on intercept and then yi minus 1 right up to yi minus p, plus there are x variables, and you can see they are kept implicit because you can have more than one x variables, and the last term is our familiar random disturbance term ui, which itself is autoregressive of order m. Since we have p lags, so we are now writing the autoregression of the autoregressive scheme of ui as autoregressive of order m. So, ui minus 1, ui minus 2 up to ui minus m, and we assume that p is greater than m. For convenience, we will take the model formed in such a way that p is greater than m. So, the null hypothesis again is that there is no serial correlation, that means rho 1 is equal to rho 2, that is equal to dot 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 rho m, and these are all zeros. So, all the rho i's are equal to 0, and the alternative hypothesis is at least one of the rho i's is not equal to 0. So, how do we do this test? We begin as usual with ordinary least squares estimates of the residuals, that is EI's, from the mother model. Now, the mother model contains yi which is regressed on p lags and on x values. So, from the equation in step 1, the first equation, the mother equation, that gives us EI's, and then as earlier, since ui depends on ui minus 1 through ui minus m, therefore, we regress EI on EI minus 1 through EI minus m, and all the explanatory variables in the model, that is yi minus 1 through yi minus p, plus all the x variables and an intercept. So, this is the auxiliary regression. So, we regress EI on all the explanatory variables in the mother model, including all the lagged values of y and all the values of x and an intercept, and that auxiliary regression now gives us R square, capital R square, which is basically the multiple square of the multiple correlation coefficient of the auxiliary regression. And since we have lagged values, so the number of observations will once again be n minus p, because we have lagged y p times, yi minus 1, yi minus 2 right up to yi minus p. So, that n minus p times R square from the auxiliary regression actually follows a chi-square with m degrees of freedom, and we can test the null hypothesis that all the rho i's are equal to 0 against the alternative hypothesis that at least one of the rho i's is not equal to 0 by finding out the critical value of chi-square m. A is the probability. So, that is the level of significance, that chi-square distribution towards the end has a tail, and after the tail it will be a% probability. So, that a may be 0.01 and then 100 times 0.01 is actually the percentage level of significance, that is 1% level of significance, or if it is 0.1 then 100 times 0.1 is the 10% level of significance. If it is 0.05 then it will be 5% level of significance. And the beauty of this is we can include not only x variables, but we can also include lagged x variables. So, that is the generalized version of the Brush-Godfrey LM test that is used to detect higher order correlation in a model which has a multiple regression format. Not only that, that model can include dependent variables as regressors. Now, finally, we take a look at one special type of feature which is called autoregressive conditional heteroskedasticity. So, ARCH, autoregressive conditional heteroskedasticity. So, that is called an ARCH model. So, here the basic idea is that the mother model as earlier, the k variable model, and ui has a variance sigma square I, where this variance follows an autoregressive scheme. So, this is conditional heteroskedasticity. So, autoregressive conditional heteroskedasticity. So, here it is a kind of interplay between heteroskedasticity and autocorrelation. There is heteroskedasticity, and the nature of the heteroskedasticity is such that we have autocorrelation among the variances. So, that is a nice feature. We call it ARCH, autoregressive, AR for autoregressive, CH for conditional heteroskedasticity. That is called the pth order ARCH process. So, by now you would have guessed the steps. What we do is we basically go for these steps. We first regress the original model using OLS, then we compute the residuals, then we get the squares of the residuals. So, EI squares do the proxy for UI, or rather the proxy for sigma square I, and then we regress EI square on EI minus 1 square, EI minus 2 square, right up to EI minus P square. So, then we regress that, and we find out from this auxiliary regression, we find out the R square, and then we compute n minus p, once again because it is an autoregressive type of heteroskedasticity. So, we lose p observation. So, we have n minus p times R square from the auxiliary regression, which follows a chi-square with p degrees of freedom, and we test it at the 100 times a% level of significance by computing the critical value chi-square p comma a, where a is the level of significance, and then we use the standard procedure. If the observed test statistic exceeds the critical value, we reject the null hypothesis, where null hypothesis is basically that there is no autoregressive conditional heteroskedasticity. Otherwise, we accept the null hypothesis. Either we reject if it falls in the critical region, otherwise we accept it. So, my dear students, that brings us to the end of the third part on serial correlation, and do go through the academic script. We will be very happy to answer any questions that you send us. Thank you.